The script for the video you're currently watching was written almost a month and a half after the previous video. While this is of course a project I only do during my spare time, I have spent a lot of those month and a half on trying to get enough progress to make another video. The operative word here is trying. At the end of the day, I was unsuccessful. So here it is, a video about what I tried, how I failed, and what I plan to do about it. The QMTech board has 256 megabytes of DDR3 memory. As you no doubt recall, I've already successfully placed a RISC-V CPU on the FPGA, taken from the excellent VEX RISC-V project, and successfully booted it using 32 of the 40 kilobytes of internal static RAM the FPGA has. What I was trying to achieve next was to break the memory constraints by using the DDR memory, giving me much more memory than I'll ever need. That was the plan. Things did not go smoothly. At all. Going into the project, I was kind of afraid of manipulating the DDR directly. I knew DDR was a complicated protocol, and I was totally content in using previously written cores for that. In the hardware world, using third-party cores is referred to as IP. I had two options on that front. The first is generated through a wizard provided by Xilinx, generating a DDR controller written by Micron, who also designed the actual chip I'm using. This IP is huge. At around 4,700 LUTs, it alone takes almost 60% of the total LUTs available on the FPGA. The other option is to use an open source IP by Ultra Embedded called Core DDR3 Controller. It claims to do certain performance trade-offs in order to be much smaller. I don't know whether those performance trade-offs are worth it because I never got either of those cores to properly work. The whole process was very demoralizing. I even posted a video update exclusively for my Patreon supporters saying, "Hang on, I'm still working on it." Speaking of patrons, I would like to extend a special thanks to Jude Deutsch. Thank you for supporting the channel and project. But through it all, I realized something else happened almost without me noticing it did. I spent most of that month and a half with several documents constantly open for reference. Those included ARM's AXI manual, Xilinx UG586, which documents the MIG interfaces, and the Micron datasheet for the DDR memory itself. This last one proved crucial. Because although it is 220 pages long, the internals of interfacing with the DDR3 memory component began to be less mysterious. I found myself more and more understanding what I'm seeing on the simulation graphs, able to cross actual behavior with the datasheet's requirements. I started to understand what's going on. And here's the thing. I think I can write a controller that will be smaller than both existing implementations. It's not so much that I am a better Verilog implementer than them, it's just that there are assumptions I can take that they simply can't. So let me cover a few of those. The first assumption has to do with initialization. The datasheet requires a certain amount of wait between power on and releasing the reset, and again between unresetting and bringing a certain signal high. You then need to set the registers in a very specific order, and then issue a calibration command with more waiting. In other words, initialization is a sequence of operations that have to happen at specific times. A hardware implementation of such a thing is done with a state machine. Problem with that is that a state machine tends to take a lot of FPGA resources. But here's the thing. My board does not need the hardware to perform the initialization. I have a CPU in the design, and as I've proven, it is quite capable of running machine code without the DDR. I can implement the initialization sequence in software. I'm not sure why neither of the implementations I've looked at use software for this stage. I think the implementers wanted to provide a closed and compact solution. That would have been great had it actually worked. The other point has to do with how memory is used versus how memory will be used by our system. I'm going to leave the most of the nitty-gritty details for another video, but the DDR we're working with reads and writes in bursts of 8 transactions, each 16-bit in length. This means that we read and write 128 bits, or 16 bytes, each time we read or write.
There are other modes of operation, but I promise to skip the nitty and gritty, and also the details. Since the CPU might wish to read or write in smaller chunks, the DDR controller has to put logic in place to tease out the correct part of the data in case of a read, or tell the DDR to ignore some of the data it receives in case of a write. The operative word here being logic. Implementing this logic takes up LUTs.
Like I hinted, there are other modes of operation that have a smaller granularity. On the other hand, to actually select these, we need logic. Which brings up the obvious question. Why is CompuSAR any different? The answer is cache.
The CompuSAR system will have the control CPU running at around 100 MHz, at least one 8-bit CPU running at around 1 MHz, and probably several I/O interfaces, all needing access to the memory at once. I highly doubt I'll manage to make all of that operate reasonably without introducing something to reduce the amount of actual accesses to the actual memory, which is precisely what a cache is for. A cache is a zero-wait state static RAM that can serve requests very quickly. Obviously, it is much more expensive, either in dollars or, as in our case, in availability, than the dynamic RAM. As such, some static to dynamic mapping needs to be used that is not injective, i.e., the same SRAM memory region needs to handle multiple DRAM regions. What matters to our current point, however, is that with cache, all transactions are of the same length and done the same way. The DDR controller need not handle the edge cases because the only one accessing the DDR is the cache, and it simply doesn't have edge cases.
Now, one might reasonably argue that that doesn't matter, that the CPU still has those edge cases, and that now, instead of the DDR controller handling them, the cache needs to handle them. To those naysayers, I say, you are absolutely, positively, 100% correct. However, A, the cache would have needed to handle them anyways, whether the DDR handled them or not. And B, the protocol for handling them with the SRAM is simpler than the one for handling them with the DDR. So there's definitely room for saving logic compared to both cache and DDR handling those edge cases, and probably even compared to just the DDR controller handling them. Writing a DDR controller from scratch is an undertaking I really didn't plan on undertaking. I was aiming for the moderate success of using an existing DDR controller over the spectacular failure of going my own route. With the moderate success turning into a moderate failure, maybe aiming for the spectacular success is the right path forward. So on that somewhat disappointing note, thank you for watching. Let's hope for happier news next time.